Welcome back to The Explainer. Today, we're diving straight into a totally fascinating problem. The way artificial intelligence is teaching mobile robots to navigate our messy, completely unstructured human environments. If you've ever wondered how a robot figures out where it is in a world built for us without constantly bumping into walls or just getting utterly confused, you are in the exact right place.
Picture this. You've got a multi-million-dollar robot packed with the absolute latest sensors and processors, and it still manages to get totally lost in a plain old office hallway. Why? I mean, it's a task most of us do without even thinking, right? Yet, for an autonomous machine, it remains this massive, complex hurdle. To figure out how we actually fix this, we're going to hit 5 key areas today: the core navigation problem, the topological solution, deformable models, evolutionary search, and finally, how robots handle tricky lighting. Let's get into it.
All right, Section 1, the robot navigation problem. Let's look at how these machines have traditionally figured out where they are.
So, there's a huge difference between the two main ways robots navigate. On one hand, you have geometric navigation. This relies heavily on odometry, which is basically doing ultra-precise math to count wheel turns and map a path. But here's the catch. If a wheel slips even a tiny fraction of an inch on, say, a slick linoleum floor, boom, the internal map is completely wrecked. Those tiny errors just snowball over time until the robot is totally lost. On the flip side, we have topological navigation. This is way more flexible. It uses identifiable landmarks, kind of like how you or I navigate. It's perfectly suited for open spaces, but it absolutely relies on a killer computer vision system to actually spot those landmarks.
Which brings us to Section 2, Topological Navigation, reading the environment.
The real future of robotics isn't about giving them a better digital measuring tape, it's about giving them much better eyes. Instead of hard-coding some rigid map, we can literally train robots to look for the exact same signs we use. Take a standard university directory board. For us, walking into a building, it's a super obvious landmark. Well, for a robot equipped with topological navigation, it serves the exact same purpose. It's a localized physical feature it can actually sense, read, and use to instantly figure out where it's standing.
And you see this with way more practical examples too. Say a robot needs to deliver a package to room 1.3C10, or it needs to find an emergency exit. It just actively scans the environment for those specific everyday signs. This completely eliminates the fear of getting lost just because a wheel slipped. Why? Because the robot is constantly double-checking its location against the real, physical world, rather than relying on an internal pedometer. It's literally reading the building.
Okay, Section 3, Deformable Models, Adapting to Perspective. Reading signs sounds great, right? But here's a massive physics problem. How does a robot actually recognize a perfectly flat, square sign if it's looking at it from some extreme angle way down a long hallway? To the camera, that square looks like a heavily skewed trapezoid. So to solve this perspective problem, researchers use a flexible bounding box called a deformable model. Think of it like a shadow stretching across a wall as the sun moves, or literally a piece of silly putty that warps and stretches to match an object's real-life perspective. Our human brains do this automatically. We know a stop sign is still an octagon even from the side. Deformable models are simply the mathematical way we give robots that exact same flexibility. Watch how this works. The system takes a basic 3D shape, like a generic cloudy blob, and it mathematically glues the visual details of a target landmark right onto it. By projecting the sign's image onto this squishy, adaptable model, the robot can basically warp it around to see if it matches any of the weird, distorted shapes hiding in the chaotic background of a room. To actually pull this off, the internal digital model uses 6 very specific mathematical degrees of freedom. It translates left, right, up, and down to scan the room. It scales to figure out distance. It rotates, and crucially, it handles perspective through vertical skew. This specific math lets the model warp perfectly to match the visual perspective of a real-world sign, no matter what awkward angle the robot is looking from.
Moving on to Section 4, Evolutionary Object Search, finding the perfect match.
Here's the thing. Searching a massive, high-def camera feed pixel by pixel for a tiny, warped shape takes an insane amount of computing power. If a robot has to freeze for 10 minutes just to process a hallway, it's completely useless to us. To fix that bottleneck, the algorithm breaks everything down into 3 super efficient stages. First, region of interest, or ROI, selection. This highlights only the parts of the image that have the right colors to be assigned, instantly tossing out the floor and empty walls. Second, it runs a complex evolutionary search just inside those highlighted spots. And third, once it locks on, it extracts the info, like actually reading the text on the sign.
Now, stage 2 is where the absolute magic happens. The system uses genetic algorithms. It's literally applying Darwin's survival of the fittest to computer vision. The model's parameters, the skew, the scale, rotation, are encoded as a digital genome. The system generates thousands of differently deformed models and tests them against the real camera feed. If a warped model doesn't match the background well, it dies. If it's a close match, it survives and mathematically breeds with other successful models to combine their traits. Through rapid generations of evolution, only the absolute fittest model that perfectly overlays the real-world landmark actually survives the process. It's wild.
Finally, Section 5, Seeing in Color. Handling bad lighting.
So we've got one last, very practical hurdle to clear. What happens when the hallway lighting is just awful or the sun is glaring right into the lens? If you just program a robot to look for the exact hex code of the color red, it completely fails the second it hits a shadow or a bright fluorescent light. This forces the vision system to process color totally differently than your standard RGB digital camera does.
To get around this, the robot switches from RGB to the HSL color space, hue, saturation, and luminance. And it relies incredibly heavily on hue, which is the perceptual color. Why? Well, because hue is highly independent of shadows and lighting changes. It keeps the true base color signature of a landmark even when the room goes super dim. Saturation helps gauge color purity, and luminance acts as a basic black and white brightness measure. By relying mostly on hue, the robot doesn't get tricked just because a dark shadow falls diagonally across a sign.
And here is the culmination of all these incredible techniques coming together in real time. Just look at the bounding box, adapting perfectly to the exact angle and scale of that stop sign. By combining HSL color filtering to beat the tricky lighting, evolutionary algorithms to search efficiently without freezing up, and deformable models to conquer the crazy geometry, the robot can confidently read signs out in the messy, unstructured real world.
To wrap this all up, I really want to highlight this quote from the researchers driving this. The combination of topological environment modeling and vision is the most promising selection for future autonomous robots. The absolute biggest takeaway from this explainer is that getting robots into our everyday, totally unpredictable lives, it's not going to happen by changing our human environment to suit their rigid programming. It absolutely relies on teaching them to read the human signs that already exist all around us. Which leaves us with a pretty provocative final thought to chew on. If autonomous robots are successfully mastering the ability to read and interpret our human world, what happens when they start leaving visual signs for each other? I mean, if they can map and read our physical world so perfectly, how soon will they start creating their own visual language that we might not even be equipped to understand? Thanks for joining me on The Explainer, and keep questioning the world around you.